harder mathematical induction. So here we're going to jump straight into an example and look at the sum from r equals 1 to n of r times ln of r plus 1 all over r. Does it equal the ln of n plus 1 to the n over n factorial? So the first thing we need to do when proving with mathematical induction is prove true for the base case. And here the base case is when r equals 1, and we can see from the bottom of the sigma notation. So we're going to prove true for n equals 1. So we're just going to get 1 times the ln of 1 plus 1 over 1. We're going to see if it equals ln of 1 plus 1 to the 1 over 1 factorial. So on this left-hand side, we've just got 2 over 1, which is 2 inside, and 1 times ln2 is just ln2. And we're checking if it equals the ln of 1 plus 1 is 2, 2 to the 1 is 2, 2 over 1 factorial is just 2, and they do in fact equal. Now we're going to assume true for n equals k. So we know our first term is ln2 on the left-hand side. Let's look at our next term by subbing in r equals 2. So we're going to get 2 ln of 2 plus 1, which is 3 over 2, all the way up onto when we sub in k. So we're going to get k ln of k plus 1 all over k. And this equals the ln of k plus 1 to the k all over k factorial. Now we're going to prove true for n equals k plus 1. So that all our first terms are going to be the same on the left. So we're going to get ln2 plus 2 ln 3 over 2. Always helps to write our second last term in when up to this step, which is just the k term. So k times ln of k plus 1 over k. Now we add in our term for k plus 1. So subbing in that for r, we're going to get k plus 1 times the ln of k plus 1 gives us k plus 2 over k plus 1. And that should equal, subbing in k plus 1 for n on the right-hand side, the ln of k plus 1 is k plus 2 to the power of k plus 1 all over k plus 1 factorial. Now from our assumption, we know all of this actually just equals this. So let's go ahead and sub that in. So let's deal with our left-hand side. So we're going to get the ln of k plus 1 to the k over k factorial plus k plus 1 times the ln of k plus 2 over k plus 1. Let's see if we can simplify this. Now we have two log terms that we need to bring together, because on the right hand side we just have one log term. So before we bring them together, we need to bring this factor out the front up into the power using our log laws. So we're going to get ln of k plus 1 to the k over k factorial plus the ln of k plus 2 over k plus 1 to the power of k plus 1. Now we have the sum of logs, which we can convert to the log of a product using our log laws. So this is all going to equal the log of k plus 1 to the k over k factorial times k plus 2 to the power of k plus 1 over k plus 1 to the k plus 1, using our index laws to also break up that power. Let's go ahead and rewrite this. So we're going to get the ln of k plus 1 to the k times k plus 2 to the k to the k plus 1, over k factorial. And let's go ahead and break up this one in the denominator as k plus 1 to the k times k plus 1 to the 1. Using the reverse index laws, now the k plus 1 to the k and the k plus 1 to the k will cancel out. And we're left with the ln of k plus 2 to the k plus 1 over, now k factorial times k plus 1 is just the same as k plus 1 factorial, and this does in fact equal the right hand side. So this is the original statement must be true by mathematical induction. So true by mathematical induction. Right, let's have a look at another question. We want to prove that x to the power of n minus y to the power of n is divisible by x minus y, where x, y, and n are integers. So if this is going to be the case, we need to set up an equation. So this will be that x to the n minus y to the n will equal some integer multiplied by x minus y, if it's going to be divisible. Now, the first thing we want to do is prove true for the base case. Should have said this is when n is greater than or equal to 1. So we're going to prove true for n equals 1. So we get x to the 1 minus 1 minus y to the 1 equals m times x minus y. So we just get x minus y equals m times x minus y, which is true where m in this case would have been equal to 1. Now, we want to assume true for n equals k. So we get x to the k minus y to the k will equal some integer q times x minus y. While we're here, we might make x to the k the subject, because we're going to use it later. So we'll say x to the k is going to equal y to the k plus q times x minus y. We should say that q is an integer. Now we want to prove true for n equals k plus 1. So this means we're going to get x to the k plus 1 minus y to the k plus 1. And we're just going to deal with this statement here for a second. So we can break this up into x to the k times x minus y to the k times y. We've already prepared that x to the k equals all of this, so let's go ahead and sub that in. So we're going to have x times x to the k, which is y to the k plus q times x minus y minus y to the k times y. What we want to do here is we're going to factorize out x out of both terms. So let's factorize out our x. That's going to leave us with y to the k plus q outside of x minus y. That's for our first term. Then factorizing an x out of this term, we're left with 1 on x, y to the k times y. And if you expanded this back out, you'd get the same thing as what we had above, because x times 1 on x is just 1. Now, let's just remove the brackets on the inside here and bring our y to the k's together. So let's leave this one. So we're going to have q times x minus y plus, so we've got these two terms left over, and we're going to factorize out y to the k. So we do that. We're left with 1 minus y on x. Let's tidy that up a little bit. So say x outside of q outside of x minus y plus y to the k. Now in here, we can tidy this up by making the 1 x over x. So they have the same denominator, so we can just subtract our numerators. And let's multiply the x back out with all the terms. So we're going to have qx outside of x minus y, plus now the x outside here will cancel with this x here. So we're left with y to the k outside of x minus y. Finally, let's factorize out x minus y, and we're left with q times x plus y to the k. And now we know that by definition in the question, x, y, and n are all integers. So, and we know k is an integer. So an integer to the power of an integer gives us an integer. An integer multiplied by an integer gives us an integer. And an integer plus an integer gives us an integer. So we can successfully say that this can be written as x minus y times some integer p, which means that we've just proven that x to the k plus 1 minus y to the k plus 1 is also divisible by x minus y. So therefore, it's true by mathematical induction.